Hi, in this lesson we're going to go ahead and get started talking about exponent rules and eventually get into polynomials. But we really need to explicitly cover the exponent rules. Most textbooks and algebra classes will go through these rules one by one, and students will get the opportunity to practice each rule in isolation. I'm not that nice. I'm going to go ahead and just throw them all at you all at once, and we're going to deal with them and pick them apart and deal with them all at the same time, because that's how you see it really in algebra. So you don't usually have them isolated in algebra, so we might as well present them all together. But first of all, I want to review again the different components of an exponential expression. So this example here of a to the n power, the a is the base number. That is your unknown number. In this case, that is our base. And then that exponent is the little number up here to the right corner is our exponent or our power, just to kind of review that with you. So something like a to the third power really means that base times itself 3 times, or a times a times a. Something like 5n to the second, that's power of 2 here, only applies to n. So that means 5 times n times n. Something like negative r to the fourth power. Now keep in mind that fourth power just applies to that r. That negative, the negativeness is like a coefficient of 1. So that this expression here of negative r to the fourth power is actually equal to negative 1 times r times r times r times r. And I guess I need to show you how that's different from something like negative r in parentheses to the fourth power. That means that whole thing to the fourth power. So that means negative r times negative r times negative r times negative r, which when you would calculate that out, that would actually be r to the fourth power. But our negatives, those negatives would pair up there, they'd pair up here, so your outcome would be positive, which has a very different outcome than if there were no parentheses. So that's just a tiny notation piece that I feel like I need to throw in here and there. But this below the line here, I'm really going to start barreling the notation, the rules for exponents. Something I want to point out is the way I've got it presented here is I am actually filling in numbers here for our examples in our powers. If you were in an algebra textbook, you'd probably have something that would look like this. N to the a power times n to the b power is equal to n to the a plus b. That's our very first rule that we're going to deal with. And students kind of wig out at that. They're like, there's just too many variables there. And so I don't do that. The other thing is we're going to be talking about variables like bases. N is our base, and here is our base. Like bases, they are the same unknown number. We call those like bases. Unlike this situation, if I had n to the a power times p to the b power, n and p are two different unknown bases, two different unknown numbers. So I feel like that's just an awful lot of alphabet to be throwing in at somebody in algebra, so I'm not going to go at it from that angle. The way I've got this presented here is I'm going to throw in actual numbers for our powers and then apply our rules as they fit. So our first rule is written here in bold. When multiplying like bases, you're going to add, and really I should remove that and put in the word collect. That's a term that we're going to be using a lot moving forward with algebra. So we're going to collect the exponents. So I have like bases. This is unknown base n, some unknown number, times some unknown number here, n, same base. That's what we mean by like bases. So I'm multiplying n squared times n to the third power. My rule says my outcome should be n to the fifth power. So basically I've written it out here, n squared times n to the third power. I can simplify that by just collecting, adding my exponents to get n to the fifth. Now this right here is just a quick little proof that I'm kind of pointing out to you. N squared really would look like this, n times n. N to the third power would really look like this. And when I write that out, so the meaning of the exponent, that kind of makes sense. I've got how many n's here? N to the fifth power. So all I was doing was just proving that. Okay, that one's pretty straightforward. The next one, we're looking at the quotient of exponential expressions. Now, n to the sixth power divide by n to the n power. What I'm doing there is I'm dividing like bases. Okay, what I can do there is I subtract the exponents. So when I look at this, I'm going to be subtracting these right here. N to the sixth minus 2 would be n to the 4th. That would simplify. I just want to prove that to you, what's going on here. N to the 6th power would be n times n times n times n times n times n. N to the 2nd, n times n. Well, if I was doing my fraction skills, I would start reducing. And I'd have everything reduced out of my denominator, so that would be n to the 4th over 1, or just n to the 4th. Well, I don't want to do that every time. This rule looks pretty slick, just recognizing that as long as I have like bases here, I can subtract those exponents. Now, if this base down here was z or some other number, they would not be like bases, and I could not do any of this. Okay, those two, hopefully, are pretty straightforward. We're going to practice a lot on these. Here I've got n to the 0 power is equal to 1. Students usually look at that and say, who the heck made that up? And what for? Nobody really made this up. It just kind of evolved. If I look at this situation, I'm going to prove it over here, that if I have n to the 4th divided by n to the 4th, this rule up here tells me I can go ahead and subtract. I'm sorry, I guess I'm doing that down here. I can subtract those exponents. So I would have n to the 4 minus 4, which is going to be n to the 0 power. So that's one way I can approach that expression. Another way I can approach that very same expression, n to the 4th over n to the 4th, is to write n times n times n times n over n times n times n times n and start reducing using your fraction skills. Everything would reduce out, and 1 is a factor of everything. So in my numerator, I'd be left with 1. In my denominator, I'd be left with 1, and that's equal to 1. And so we're like, well, wait a minute. I've got the same expression, and I came up with two different solutions. It must be, no matter what approach I take, these two expressions have to be equal to each other. So n to the 0 must be equal to 1. So again, all I was doing over here was proving it, that any base raised to a power of 0 is going to be equal to 1. And so you'll kind of get to the point where you just kind of recognize that. Then you're going to think, really, do they have to put negatives in the exponent level? Yes, n to the negative 2 is equal to 1 over n squared. Basically, that negative at that exponent level is just meaning that base is in the wrong place. And so you have to move it. If it's in the numerator, you move it down to the denominator. If the negative exponent was in the denominator, you'd move that base up to the numerator. So a negative exponent places the base in the denominator, and I should say vice versa. But I want to prove to you how that happens. So again, I'm going to have two different approaches. This n to the 3rd means n times n times n. N to the 5th means n times n times n times n times n. I can do my fraction skills and start reducing, and I'm left with n times n, or n squared, in the denominator. So that's one way to simplify that, this whole expression. Now I can take that same expression, n to the 3rd over to n to the 3rd, and apply this rule up here with the dividing like bases, which means I would be saying n to the 3rd over n to the 5th would be n to the 3 minus 5. I'd subtract my exponents, which would mean I'd have a negative 2 here. So it looks like I came up with two different solutions here, but really I'm just proving that these two expressions must be equal to each other. Okay, moving on. The last two really seem pretty logical. So I've got this, really what I'm doing here is I'm raising a power to a power. I have m squared, and then that is cubed. That is the only case where I'm going to be multiplying exponents. So m squared cubed really is equivalent to the m 2 times 3, which would be m to the 6th. So what the rule states is that when you're raising a power to a power, which is what you're doing there, you're raising m squared to another power cubed, you're going to multiply the exponents. So again, here I'm just kind of proving it, that m squared is just m times m. Cubing that means I'm taking that 3 times. And so you can see I'm multiplying all this together. I'm left with m squared. So we just kind of proved that. You wouldn't want to write this out. This is a much easier rule just to automatically apply. Okay, so the last two are really the same rule. When you're raising a product or a quotient to a power, you apply the power to all bases. So in this first one, I've got a product of m times n. You can kind of look at that as distributing that back. You just need to make sure that you cube both of these bases, or apply that power to both bases. So that would be equivalent to m cubed, n cubed. Same here when I'm dividing, or I'm looking at a ratio or a fraction that is cubed, I would be applying that cube, or whatever the power may be, to both the numerator and the denominator. Would it be equivalent to n cubed or over m cubed? Okay, at this point we could go ahead and do some practicing, but I think I'm going to run out of video time, so I will start that up in our next video.